in this presentation, I would like to talk about implementation and one of the prediction models that we designed for Tennessee Department of Transportation, and some of the future work that we hope we can do it, but other people, if they are also interested, they can do it as well. This is the general pipeline that we designed. It looks scary, but I will go through the detail. So the first part, as I mentioned in my first presentation, is data collection. So we get data from various resources. So for example, we get the accident data from Tennessee Department of Transportation. Then we get the weather data from 2 resources, but we chose the one that we thought is better. Then we have the traffic data, which we are collecting from NRIX. And then we have the roadway segments, which also we are collecting from NRIX. And we have to combine them, we have to aggregate them. And after this process, we will have the combined data frame, but a little bit more details that what might be the challenges in selecting the data. So for example, this is one of the examples about the roadway segments. Originally, we were collecting the data from ERMs, which is another resource, but you can see the ERMs roadways in green, and you can see the NRIX roadways in red. And you can see like NRIX roadways is covering more roadways compared to ERMs. And while we have, and the blue dots are showing the incident. So because of that, because of the coverage, so later we switched to NRIX for higher accuracy. This one is about elevation. So we believe one of the important features in accidents, it can be the elevation changes in the roadways. And for example, here you see a bridge. On the left, you see from the map, and on the right, you see like a 3-dimensional picture. But when we collect the data from elevation resources, for example, USGIS, for example, Google Maps Elevation API, this is what you see. And the problem here is usually these data banks, they work as a function, one-to-one function. So usually you have a coordinate, you give that coordinate, and you get just one elevation for that specific coordinate. However, in a case like a bridge, you have 2 coordinates, one on top of the bridge, one below the bridge. So this is, for example, another details in data collection that you have to be aware of it when you're doing that. Interestingly, actually, Google Maps is aware of the situation. So for example, if it ever happened to you that you're biking and you want to know the elevation, Google Maps is aware of that. So technically, it knows you're going above the bridge and you can see it, and you're going under the bridge and there is no like bump here. For some reasons, probably Google Maps doesn't want to share that information with you through the API. So if you're collecting that data through the API, you don't see such a thing. So what we've done is, this is also more details information, for example, from USGIS, from Google Cloud Platform, and from the LiDAR that we have from Tennessee Department of Transportation. So what we've done is highways, they have a limited slope based on OSHTA, which is the standard for highways. So whenever we see a slope more than 5%, we consider that one as an anomaly. We get rid of it and we try to replace it with interpolation. We had some hard problems with the weather data as well. And you can see, for example, dark sky, that was the first source that we used. But later we switched to WeatherBed for fewer number of missing values. And for example, we have multiple stations. And so for now, for example, we map each segment to the closest weather station for using the weather station for that segment over time. However, maybe later more accurately can be if we train spatial correlation methods such as kriging or Gaussian regression, then we're going to have like a shell for the temperature, or for example, for precipitation on the map, and considering the spatial correlation. But considering like 40 stations for the state of Tennessee, I think we have enough data which we don't need for a more accurate modeling of the spatial correlation of the weather. But if your stations are fewer and your space is bigger, your spatial dimensions are wider, so you may need to do that. And then that was the incident data. So for example, this is the incident data that we get, and you can understand, you can guess how much data cleansing that we have to do on this data. This incidents were supposed to be just incidents on roadways of the state Tennessee, but you can see there's all over the map. We have some other problems. I move on for the sake of time, but for example, the timing was a little bit problematic at the beginning. So probably you have a big challenge for data collection, data cleansing, aggregating the data. And here, for example, you can see all the incidents in the state of Tennessee that we have access to it right now, but not all of them are of interest. If we are trying to, for example, predict the accident rates for highways, so the ones they occurred on a highway segment matters to us. So this is just summarizing this table of summarizing the data that we used. You can see the size of the data, for example, the traffic data. So without cloud resources, it's virtually impossible to do this type of research because of the amount of data that you have access to. So the first module, or most of it, is about just collecting the data, combining the data, and aggregating the data. Then after that, we have two important modules. One of them is the clustering and the resampling. So the idea of clustering is putting the segments that we believe they are similar together. There are various ways to do that, but the main idea is, so for example, these are the highway segments between the big cities in the state of Tennessee. So we try to put them together because we believe they have the similar behavior, compared, for example, to a highways going through the downtown of a big city like Nashville. There are various methods to do that. The caveat is clustering is helping the model to learn the pattern easier. However, when you cluster the data, then you're technically breaking the number of the samples to a smaller baskets, so which limited the number of observation for the model to learn. So for example, we use this agglomeration clustering. We also use k-means. And for example, again, just some more details is the connectivity in agglomeration clustering can be useful. So you can see, for example, here, if connectivity is not being used and if connectivity is being used, these two are close to each other in terms of similarity distance, but they are not connected. So if you use the connection, this type of clustering doesn't consider them as the same cluster. Another thing that we did was the resampling thing. It's also very common to address the problem of sparsity in the data. It's try to either oversample the minority class or undersample the majority class. If you have a lot of zero data, for example, you can do undersampling, but undersampling is getting rid of some of the useful information. And oversampling is just repeating some of the class one, for example, the minority class in your data set. There are some other methods like SMOTE, for example, that can be used. And after that, the data is ready for our machine learning models. So there are various models of logistic regression and ZIP. They are very popular in the transportation community. And as I mentioned in my earlier presentation, neural network and the tree models, if you have enough data, they are wonderful methods to be used. You have to be aware of the overfitting, but other than that, they can be very useful in prediction. And this can be considered as the new trend right now. And we use them, we do some hyperparameter tuning. And we also have the base model, and the base model here is like the average of the state. It tries to imitate what is currently being done by the Tennessee Department of Transportation in terms of predicting the accidents and next step allocating the responders or response chart. And in general, you want to consider randomness, to the same model with the same input, the same neural network, it may give you a slightly different output at the end because of the inherent randomness in the model. So to consider it, usually you want to do multiple test and train data set and take the average to do that. And in our case, we were just using, for example, a rolling method. And in this specific figure that you can see, we used this April 2017 to January 2019, the red month technically, to predict the February. And then we add February to our training data set to predict the March. And this is very important because technically this test cannot be in the middle, right? Because you always use the data you have or you had in the past to predict something in the future. And so after having multiple test and train, we can choose the best model of interest. And of course, again, there is a trade-off between the complexity of the model and explainability of the model. So neural network can be great, but they are more like a black box, which makes the explaining of the model to the client or to the Department of Transportation a little bit harder. And then when everything is done, when everything is ready, we chose the best model. Then we have a prediction module. This prediction module technically tries to collect the data, for example, the weather data from the future, use the train model to predict the dangerous segments in the future. So this is like, I can tell you, this is a way of presenting the data, the prediction data. On the x-axis, you see the time. So for example, here we have a 4-hour time resolution, which we are trying to predict the likelihood of accident. And this one is the spatial segmentation. So for example, these are just some names for the segments. And the color is showing the likelihood. And here you see the clusters. For example, here I think I have 9 clusters from dark green and purple to yellow. And these are like the marginal distribution. So for example, based on that, we can see which days they were like more dangerous. So probably this bright ones, they are more rush hour, 4-hour windows. And here you can see which segments on average they are more dangerous. It's the marginal on the segments. And here, for example, you can see the prediction on a spatial map. So which segments they are more dangerous in the prediction, and it will change over the time, of course. And this one is, for example, showing the clustering of how different clustering or different clusters are distributed on the map. And after that, so the important part is the simulation. So if we have multiple methods and we are using machine learning metrics to tell which method is better. So for example, if I tell you this method has a better F1 score, it may not be very tangible. So the best thing that you can show if a method is better or not is just try to apply it in a real world and to see how it will react. So in this case, we were trying to come up with a simulation, which just trying to imitate the actual scenario. And the actual scenario is usually like this. They are limited, a few number of trucks. They are strategically distributed on the map by the experts, by the engineers. The first accident happened. The closest responders, as Ian mentioned it earlier, is being dispatched to the accident, and it wouldn't be available for example, a service time like an hour. The second accident happened, but the closest is busy, so we dispatch the second closest available to that accident, and the process goes on and on. And the goal is just minimizing this blue arrows that you can see. So we want to be on the scene as fast as possible. And allocation, as Ian mentioned it, again, allocation has different strategies, but here we are just trying to do a simple one just to evaluate the models, the prediction models. And we came up with this. There are some details in it, but for now, I just skip it. And the way that the simulation works is, for example, the one below is the base model, and the one on the top is the suggested model. And based on the prediction, we distribute the trucks on the map. Then we see what happens and measure the travel distance by the responders. Then we do it for each, for example, 4-hour window or each day or each month, and we calculate the results. And that part was the simulation. And then based on that, we can compare different methods. So the method has a lower travel distance or has lower service time. Generally, it's a better model. These are some more details about how we present the model. We use Docker. These are some more details about it. For now, I skip it, but if you're interested, I will be available later to discuss it. So for now, our pipeline is about 10,000 lines of code, and you can see some measurements about the size of the project. And some of it is available, publicly available. Some of it will be available later through GitHub or through our website, Statras. But some of the future work is, first one is the graph neural network. We are really interested to apply it. We have seen some research. They are using the graph neural networks for traffic prediction. So we thought that might be a good idea to use the same approach for incident prediction. Another one is the transfer learning. So for example, California may have a longer time range for recording the accidents, for example, 10 years, but Tennessee is, for example, 3 years. So why don't we train a model in California and then transfer the model using the transfer learning approach to Tennessee? We already have a paper that almost you're using the same approach for predicting the energy prediction of EV vehicles. So we are trying to use the same approach this time for incident prediction. In my first presentation, I talked about detection and prediction. So why don't we combine this too? So if Waze, for example, is giving us very useful information about the location and the time of incident, and our historical data is showing the same thing, our prediction model is also giving us a high likelihood. So why don't we combine them and come up with a more accurate method for prediction? Another one is the model stacking, which also mentioned it in our presentation. We use different models, logistic regression, neural networks, different actually architecture of neural networks can be used. So that can be another machine learning on top of that to improve the results. It's worth mentioning, we need data for that. We don't want the model to be too flexible to overfit to the data and not being generalizable. That was my last slide. My apologies if I went so fast through it. I just wanted also to make some room for a little bit for discussion and any questions that that you may have. But thank you so much again for your time and attending this panel.
If anybody has any questions, feel free to ask. Also, as Syed mentioned, a large part of our work is open source. If you are working with multi-agent systems or machine learning for any sort of spatiotemporal incidents, because these are quite generalizable, feel free to reach out. We are always looking to collaborate. We'd be happy to help. Yeah, I mean, if you're interested in any of the papers, we'd be happy to share a draft or our implementation. And thanks again for attending the tutorial.